Okay. Okay, everyone. So today is what? May 12th. So this is the last lecture of the class, and I'm going to give some information about the final, which will be on May 15. And after that, if you don't have any questions, I'll just go to the last section, which is compound interest. Okay, so in the email that I sent you before, I said that the final is optional. So if you're satisfied with the grade I sent you, which is your current grade, and I explained how I calculated it there. Well, if you're satisfied with that grade, then you don't have to take the final. The final is optional. Oh, by the way, also the homeworks for section 5.1 and 5.2 are also optional. I told you in the beginning of the class we will have 14 homeworks, so that was until section 5.1, not including. So, and also the lowest two grades were supposed to be dropped. I'm actually dropping lowest three homeworks. So okay, so the homeworks for sections 5.1 and 5.2 are also optional. Okay, so regarding the final, so the final will be on Friday, May 15th. It will be at 8 o'clock in the morning, your time. It will be approximately 2 hours and 30 minutes. Okay. And it would be very similar format like midterm 2, meaning that you have to turn on your cameras and solve, and then um, send me the pictures of your final. So what is the final going to be like? So it's going to consist of 10 problems. These problems will be chosen from all sections that we covered. So they will cover all the way from the very first sections until the compound interest. And if the homework is if the final is submitted, then it will be counted towards your uh, final. Okay, so you cannot just take it and decide, okay, I wanted not to take the final. If you're taking, then you're taking. I'm gonna count it. Okay, so there will be only one problem about compound interest. So 9 problems will be 90% of the test will be about the material that was covered in midterms 1 and 2. So everything up to until midterm 2. So 90% of the points will be from things which are not compound interest. Okay, so there will be a practice test which I will send out to you today. The solutions to this practice test I will send you on Wednesday, so tomorrow, hopefully before evening. And during the review session on Thursday, I'll go over some of these problems. I don't know if I will have time to go over all of them. Okay. So during the midterm, during the final, you can use one sheet of notes, and so it's as usual handwritten notes, two-sided letter size, so 8.5 times 11 inches, and you can use calculators as long as you're not doing some graphing or things like that. Okay. So are there any questions? Okay, if there's no questions, I'm going to go go ahead and talk a little bit about compound interest. Okay, so what is compound interest? What's the problem? The problem is you're trying to figure out the main thing is to figure out how much money you have in a bank account. If you know that what you're investing, what's the annual rate, and what's the time limit. Okay, so suppose here is a simple example, right? So suppose you invest $10,000 in an account, in a bank account, or some sort of an account, with the annual rate, with the annual interest, or let's say yearly interest of let's say 5%. Okay, suppose you know that. So so the question is, how much money will there be in the account after certain amount of time? Okay, so after say 5 years, maybe 10 years, 10, 20, okay? So any of those things. So we want to have a formula which will tell us that if you invest certain amount of money, then you're going to get how much you're gonna get after certain amount of time passes. Okay, so so let's try to first figure out how much I will have after 1 year. So if I have, so initially I have $10,000. So after 1 year, well, I will have 10,000 plus 5% of this 10,000, right? 5% of 10,000. So what that means is that 10,000 plus what is 5%? It means that 10,000 you multiply by 5 and then you divide by 100, right? So 0.05 in other words. So let's just write it like that. 10,000 plus 10,000 times 0.05. So if you do the computation here, I'm going to cancel this and this. So I'm going to get $500 there. So it's going to be plus $500. Okay. So that's going to be 10,500. Okay. So let me do this calculation a little bit differently, actually. So let me rewrite this a little differently here. So I'm gonna write this is the same thing as 10,000. So forget about the fact that I canceled those zeros. So I have 10,000 plus 10,000 times 5 over 100, which is 0.05. So if I factor out the 10,000, I'm going to get what? I'm going to get 10,000 times 1 plus 0.05, which is the same as 10,000 times 1.05. Okay, So that's the amount I will have, which is of course the same as 10,500. Okay, so then the question is, how much will I have after 2 years? Well, after 2 years, I will have, it's the same thing as I put 10,005, whatever I have at the end of the 1 year, and then I add 5% on the top of that. So how do I calculate that? So I'll write after 2 years, I will have, well, how much I have at the end of the first year? I have 10,500. And what am I gonna get? I'm gonna get 5% of that added at the end of the second year. So it's going to be 10,500 times 5%, which is again 0.05, right? Okay. So if I simplify, this is gonna get 10,500. I can factor out this common term again. So I'm gonna get 10,500 times 1 plus 0.05. Okay. Or if you want, yeah, let's just keep it like this. So, but this is our correct answer, but I want to write it differently. I want to write it like this. Well, let's see, what is 10,500? Well, that's this number here, which I can also write as 10,000 times 1 plus 0.05, right? So this thing here is the same as this thing here, right? Right? I just rewrote it differently. That was the amount after 1 year. So if I use that, I'm gonna get the yellow part is going to be 10,000 times 1 plus 0.505. And then I have this other 1 plus 0.05 as well. So I'm just gonna write that again. So it's going to be 1 plus 0.05. So the whole thing is gonna be 10,000 times 1 plus 0.05 squared. Okay, so here is the formula that I obtained for what happens after 2 years. So after 1 year, I'll have 10,000 times 1 plus 0.05 with the power 1, right? So, and after 2 years, I have the same thing, but with the power 2 here, okay? So in general, so the formula becomes after t years, we have that the amount in the bank account would be 10,000 times 1 plus 0.05 to power t. Okay, so that is the amount of money in the bank account after 10 years. T years. Okay, so if you wait 1 year, it will be just 1 instead of t. If you do 2 years, then you will have 2. So the only thing that changes with the time is this thing here is the time, t. Okay, so this is, so for instance, if I do so 2 years, then I will have a square here and I can do the calculation. So this is a very general formula. So the formula becomes this. So for the in general, we have this formula. So A is equal to P times 1 plus R to power T. So let me explain what this formula is. So this formula tells you how much money you have in your bank account with the following conditions. So if here P is the principal amount, right? So this is the initial, what's the question? There was a question. Sorry, I'm like, what's the deal with the final? So if you look at the recording, there's going to be explanation of that, but I also send an email. So I'm recording this now, so let me answer all the questions about the final at the end of the recording, okay? So, okay.
Nah,
So I'm gonna answer all the questions about the
I don't
final.
really understand how you could do that, because
Hello?
like it's not even fair, truthfully. Because if you're gonna
What?
do that, like you gotta really be ready for the consequences. You know what I'm saying? Like honestly,
Francis, are you talking to me? I guess I shouldn't be ready for the consequences. Um, okay. So in this formula, um, in this formula, we have P is the initial amount, R is the rate, so that's the yearly interest rate, right? So this is yearly interest rate, and T is the time, okay, or the number of years of years, and A is the what you get in your account, so amount after time t. Okay, so again, so what does what this formula represent? This formula represents the amount of money in your account if you put initial amount P and the in and the account accrues R%. So the interest rate is R for 1 year, and T is the time. That's how much, how long you have left the money for. Okay, so this is what's used all the time. So that's called compound. The formula for compound interest. So if you didn't, so what's the difference from putting certain amount and then not having, so what happens in the previous problem, let me show you. So what you did is you put $10,000 in your account, and then you have 5% after a year, so you have $500 at the end. So it's possible one scenario is that every year you would get $500 added to your amount. Okay, but what that means is that's not the same as what we're doing here, because in this thing, what we get is we get interest on this $500 as well. Not only on the initial amount, but also on the $500. So what you get is you get interest on interest. And that's why the word compounding. So you get compounding of the interest, okay? So, and there is a big difference between the two things. So let me just show you an example. So if there was no compounding, so let me just write here. So without compounding, what you get is A is equal to the principal amount, then you add, so you add certain percentage, so that's P times R. Actually, let me just write it as a formula like this. 1 plus T times R, okay? So this one, so the amount in your bank account would grow like this. That would be without compounding, and these are very different things. So this one here and this one here are very different. So again, what's the difference? In this situation, you don't get interest on interest, so the interest does not compound, while in this situation you get interest on the interest and the interest compounds, so you get more returns. So let's just compare the two things. So let's, in order to compare, first let me make this whole thing a little smaller. Okay, so here's an example. Let's assume that we're, so example. So again, let's take, suppose that initially I put $10,000 in an account. So that's my P. So the rate is 5%. So it's 5%, or if you want, it's 0.05. And let's say I'm putting the money for 30 years. Okay, so let's see what happens to the account after 30 years if I use this formula first. So let's assume I'm using this. So I get 5% of the 10,000 added every year. So, so without compounding, let me make this bigger. Okay, so without compounding, we get after 30 years we get this. A is equal to, so this is the formula I'm using, right? So that's the formula. So it's going to be P, which is 10,000. So I'm going to write 10,000 multiplied by 1 plus T, which is the number of years. So that's 30 years. So that's 30 times 5%, right? So 5% is the rate, yearly rate. So it's going to be 0.05. Okay? So if I do the calculation, I'm going to get 10,000 times 1 plus, well, 30 times 0.05 is going to be 1.5. So the whole thing is going to be, this is 2.5. So 2.5 times 10,000 is going to be 25,000. Okay, so that's what I'm going to get if I don't have any compounding. Okay, and let me make this smaller again. Okay, so I have space and I can compare the whole thing here. Okay, similarly, so now I'm curious about what happens if I do with compounding. So with compounding, we get this. So we get this other formula that we had on the top. So that's this one here. So let's use that formula instead. So I'm gonna get A times sorry, A is equal to P, right? So the formula is, let me write it again, P times 1 plus R to power T. So let's use that formula. So again, I'm gonna, initial amount is going to be 10,000. Then I take 5%, right? And then I raise that to power 30. Okay, and let's see what happens. So, well, what's that? That's 10,000 times 1.05 to power 30. So let's see, I'm gonna check that on the internet. So I'll do the calculation. Okay, so it's 10,000 times 1.05 to power 30. Okay, so what we got is 43,219. Okay, so that's approximately, of course. So there is a huge difference. Okay, and you can actually, if you take like larger percent, you get a very different, a bigger difference. So again, what did we get? We get two answers. So without interest, without compounding, we get that, and with compounding, we get 2 times more, almost. Well, not 2 times, a little less than 2 times more. But the idea is that these are very different functions. So what's the difference? Here I have a linear function, while this one here is an exponential function. So if I draw them on the same graph, I'm going to get these pictures here. So if, say, this is 30 years or something like that, right? So maybe that's 30 years, you put certain amount. If you have no compounding, your function would look like that. And if you have compounding, actually it would look like this, like an exponential function, right? So this is no compounding, and this is with compounding. So this is an exponential function, and this is a linear function. Okay, so when you put some money in a bank account, it usually grows exponentially. Similarly, if you have a like a loan or something like that, I mean, it's the other way around. You get the bank takes from you certain, like, it's usually using exponential models. Okay, but so similarly, there is one thing which I want to ask. So let's look at the formula again. This is the main formula for today. That's this thing here. Okay, so I'm just going to write that again. So that's the main formula, which is A is equal to P 1 plus R to power T. Okay, so so this is the amount if you get the amount in the bank account, where P again is the initial amount, R is the rate, and T is the number of years. However, usually what the banks do, they don't, they do what's called compounding, not just once a year, but several times a year. So for instance, if you take, if you invest, so this, maybe I should write this down. So this is compounded once a year. Okay, once a year. So what if they want, what they usually do is they don't really compound just this 5% at the end of the year. What they do is, so for instance, if your yearly rate is 5%, they compound maybe more than once, like they can compound during the first half year and then during the second half of the year. So what that means is that your initial amount, which in this example was 10,000, it's going to be added not 5% during the first half year, but 2.5, which is half of 5%. So, and then another 2.5% during the second half of the year. Now, this may seem like it's the same thing, but it's not exactly the same thing, because so the formula at least is going to look a little different. So what's going to happen is you do, so if you compound twice a year, so the formula will be A is equal to the principal amount times 1 plus, now you take the rate and you divide it by 2, so that makes sense, right? Instead of compounding once with 5%, you compound twice with 2.5%, but then you raise to the power 2 times t, okay? So that would be the formula if you were to compound twice a year. And similarly, if you can compound 3 times, 4 times, 5 times, or any number of times, so compounding let's call m times, gives you the formula, which is this one here. A is equal to P times 1 plus R over M to power mt. So the most common thing that you see is maybe you can have compounding once a month. So this m could be 12, right? So this is the number of times in a year that you are compounding, okay? So, but I mean, sometimes, so what's the difference? The difference, there is a difference, but sometimes it's not very large, very big, the difference, okay? So sometimes they take m larger and larger. So when you take m larger and larger, so you basically take the limit of this expression and take m to infinity. That's called continuous compounding. So that means that the amount is compounded basically every second. It's continuously compounded. So for continuous compounding, you have a little bit of a different formula, which is very similar, but it's obtained from this one. So continuous compounding. And the formula for that is this. So you take A, again, you take the initial investment, and then what you do something different. You take this exponential and you raise it to power RT. Okay, so that's the formula for continuous compounding. So why would we use this formula? It doesn't look at all similar to this. Well, in some sense it doesn't, but in reality it turns out that if you take limit of this expression here as m goes to infinity, then that's what you get, okay? I'm not gonna talk about this much, how you get this, but just take it for granted that if you take this compounding, right, formula, so this is the one which is for once a year, this is m times a year. Now if you take more and more, so you have this continuous compounding, you get this formula here, where again e is the exponential, e is the usual exponential. So e is the exponential, right? So it's this special number that we talked about when we talked about natural logarithm. So it's approximately 2.78, etc. Okay, so those are the two formulas which will be useful for us. So this one here, that's used for continuous compounding, and well, I won't really do compounding more than once a year, so I will just use this one here. So those two formulas are the important ones, this one here and this one here. Okay, so now let's do some problems. So I'm going to write these formulas again and do some problems. Okay, so so we have these two formulas. A is equal to P times 1 plus R to power T, and A is equal to P times E to power RT. So these are both formulas for compound interest, but in this case here, this is compounded once a year, and this one is compounded continuously. Okay, so let's use these formulas to do some problems. So here is an example. Suppose you invest I don't know, certain amount. Let's do $20,000, right? Or actually, let's do $5,000 in an account. With the the yearly rate of, let's say, 10%, right? Okay, so how much will there be after, let's say, 30 years? Or I don't know, 20 years or 10 years or something like that in the account. So, and then, so one of them, so assume you're compounding once a year, and the other example, let's do compounding continuously. So, so let's see, if the account, if the money is compounded once a year, and the other situation will be continuously. Okay, so both of them. So that means we're using just these two formulas upstairs here. Okay, so let's do part A, which is once a year. So A. So again, so what we have? We want to find this A, and what is it that is given to us? So the principal, or this initial amount, is $5,000. So I'm going to write here $5,000, 5,000. Then I have to write 1 plus R, right? So R is 10%, right? So R is, R is 10%. So that's just 0.1. So I'm just going to write 0.1. And then T is, right, 30 years. So I'll just do 30 here. So 30. So if I solve this, this is going to give me 5,000 1.1 to power 30. So my answer is going to be, okay, let me do that. So 5,000, 1.1 power 30. So it's going to be quite a large amount. So it will be 87,247. Okay, approximately. Okay, so in 30 years you get that amount, so that's actually quite big. So almost 10 times your amount grew. So if you add it, actually in this case, if you, so let me just compare here. Let's make a comparison. So if there was no compounding at all, how much money would you have? So let me write it here with blue. So without compounding, would have would have 5,000 times 1 plus 0.5 times 30. So that's 5,000. 1 plus 0.01 times 30 is 3. Later, okay? Okay, my daughter wanted this to show you. No, no time, okay? Later, okay. So 5,000, 1 plus 3. So was there a question? So it's 4 times 5,000, which is 20,000. Okay, so that's a huge difference, right? So 20,000 and you have almost 90,000. So after 3 years, so that's the difference between linear and exponential growth as well. Okay, so but if you have bank account, it's usually earning a compound interest. Okay, are there any questions about this? Okay, so if not, I'm gonna do the same so let me go over this one more time quickly. We have the amount that's invested. This is the initial amount, and it's 10% rate, so it's 0.1 for 30 years. So that's what you get. So you get 5,000 times 1.1 to power 30, and that's what you get. Okay, very similar to this, we can do continuous compounding. So continuous compounding, then we will be using this other formula, right? E to power RT. So I'm going to write A is equal to, again, initial amount is 5,000 times to power E R to power RT. So R is 0.1 times T, where T is 30. So it's going to be 5,000 times E to power 3. So let me calculate that. So that's going to be 5,000 E to power 3. Okay, so that's going to be actually a larger amount. So this is approximately 100,427. Okay, so so what is this again? This is the amount you get if your money is compounded. Not, it's still with 10% annual rate, but it's continuously compounded. It's not compounded once a year, right? So you wait a year and then you add 5%. You wait a year and then you add 5%. Now, what you do is every Second, you add, of course, not 5%, a very tiny fraction of the 5%, but everything adds up. You get all this interest on the interest, and of course, what you get is better, a larger sum. So here you get what's called compounded once a year, and here is what you get if you do compounding continuously. Okay. Are there any questions? So let me go to different problems. So I want to do two more problems, and so the second problem is very similar. So this is an example. We want to find out how much do you need to invest now to get to a certain goal in a certain amount of time. For instance, here, okay? So the question is, how much should you invest initially, right? So in an account earning let's do again 10% a year, right? Okay. If so that you have, let's say, 100,000 in 10 years or in maybe 20 years. Okay, so this is a natural question. So suppose you have a goal which is to have $100,000, okay, and you're giving yourself 10-20 years, right? So 20 years you want to have 100,000, and you know that this account is earning 10% a year, right? So suppose you're investing in the stock market and things like that. Okay, so how much initial amount should you invest in your bank account? Okay, so and then there's again two situations. One of the accounts is compounding once a year, the other one is compounding continuously. So I'm going to do A, compounding once a year, right? So in that case, again, my formula was A was equal to P times 1 plus R to power T, right? So in this problem now, what's given and what is it that we want to find? What is the amount that we're trying to get? That's 100,000. So that's what? That's not the initial amount. That's what we get here. That's our goal. So I'm going to put A here. What we need to find is this P here, right? So if you plug all the information that's given to you, again, A would be 100,000, so it's 100,000. That's equal to, so P is the initial amount which you want to find out, so P, and then you multiply by 1 plus, okay, what is the rate? Rate is 10%, so it's 0.1. And then T is the number of years, so I'm going to write here is 20. Okay, so in this equation, all I have to do is find P, right? So let's actually simplify this a little bit. This is going to be P times P times 1.1 to power 20. So if I want to find P, I'm gonna divide both sides of this equation by this number. So it's my P is going to be 100,000 divided by 1.1 to power 20. So if you want, we can write it differently. 100,000 times 1.1 to power negative 20. So if I solve for this, I'm going to get the following. So let me just write it down. So I have 100,000 e to power negative, well, actually not e, but 1.1 to power negative 20. That gives you, okay, so 14,000 approximately, 14,864. So that means if you want to have 100,000 in a bank account that earns 10% a year in 20 years, right now you need to invest approximately $15,000. Okay? In a very similar way, I can do the same thing for, so that's this here. Very similarly, what I can do is what happens if I compound continuously. So okay, so then I have that the amount is equal to, again, P times e to power RT. So again, I know all the numbers here except P, so I'm just gonna plug them in. So I'm gonna get, I want to have 100,000. So the initial amount is P. I want to multiply by e to power R, which is 0.1 times, and t is 20, right? So this is going to be P times e to power 0.1 times 20 is 2. So therefore my P is going to be 100,000 divided by e squared. So let's calculate that. So that's going to be 100,000 divided by e squared is equal to, it's approximately 13,533. Okay, so well, that makes sense, right? Because continuous compounding is better than compounding once a year. So initially you need to invest less to get the same amount. So since this continuous compounding becomes bigger faster, so to get to $100,000 in the same amount of time, you need to initially invest smaller with a scenario which gives you a faster growth, which is continuous compounding. Okay, so are there any questions? Okay, so if there is no questions, I'm going to do one more problem about these accounts. And then we will be done with this, with compound interest. So the next example is the following. So suppose you have certain, so it's a little different. So suppose we have certain amount of money and we want to get to, we know that what's our goal and we know what's our well, what is the rate? The question is, how long do I have to wait for that? Okay, so that means, so how long do I have to wait to to get say, let's say 100,000 to get 100,000 in an account. By if I initially invest, say, I don't know, $5,000, and let's say, I don't know, 8%. Okay, so 8% is the average. A lot of the times that's the average of the how stock market grows. So suppose you have $5,000, you're investing in an account which earns 8% a year. How long do you have to wait to get to 100,000? Okay, you can change this problem to make it different. Initial investment principles and the different goals, and also you can have different rates. So let's do this and use the formula. So I have A again is equal to the principal amount times 1 plus the rate to power t. So what is it that I want to find in this problem? I'm given the final amount, my goal. This is my initial amount. This is the rate. What I want to find is the time required for me to reach that goal. Okay, so so that's what we're going to do. So let's plug in the formula, the numbers. I have 100,000. Of course, this is the scenario where I'm compounding once a year. So it's 100,000 is equal to 5,000. That's my initial amount. And then you have 1 plus 0.08, right? That's 8%. And then that's to power t. Okay? So what I'm going to do now is I'm going to try to find t. So we want to solve for t. Okay, so what do? I'm gonna collect all the terms which have t on one side. This is the term right here. Now I have, so for that I'm gonna divide both sides by 5,000. So I'm gonna divide by 5,000. So I'm going to get 100,000 divided by 5,000 is equal to 1 plus 0.08 to power t. Okay, so what's this? 100,000 divided by 5,000, that's 100 divided by 5, which is 20. Okay, so I have that 1 plus 0.08 to power t is equal to 20. Let me rewrite this as 1.08 to power t. And then I have this equation, which is 20 is equal to 1.08 to power t. Now, how do I solve an equation like this? Well, that's what we did last time when we were talking about logarithms. So what we're going to do is we're going to take natural logarithm of both sides. Doesn't have to be natural logarithm, it could be any kind of logarithm with base 10, any base. Okay, so let's do that. So I'm taking logarithm both sides. Okay, so I'm going to get, let's do natural logarithm, okay? So I'm going to get natural logarithm of 20 is equal to natural logarithm of 1.08 to power t. However, if you remember, natural logarithm has the property, any logarithm has the property that if I have a power, then that power comes to the front. So I can write this like this. I can write that natural logarithm of 20 is equal to t times logarithm of 1.08. And there you go. You can just find t by dividing both sides by this constant here. Okay, so I get that my t is equal to logarithm of 20 divided by logarithm of 1.08. And that's a nice illustration how logarithms are used. So let me just calculate this number. I'm gonna get logarithm of 20 divided by logarithm of 1.08. So that's 38 approximately. 38, where is that? 38 point, yeah, almost 39. Okay, so so it's approximately 39 years that you have to wait if you invest 5,000 and you want to get 200,000. Okay, if you have 8%. Similarly, if you had an account which was doing 10%, then it would be much actually shorter. So if you did 10%, then your answer would be 30 years. But so like by just 2% different reduces the amount by actually 8 years. Okay, so it looks it looks like the percentages don't play such a big role, but just by reducing little, changing the percentages a little bit, you're gonna get a big difference. Okay, so are there any questions? If there is no questions, then I'm gonna stop recording here, and then I'm gonna answer all the questions about the final and related things.